Welcome to the fourth lecture of the course Applied Stochastic Differential Equations. In this lecture we'll learn about numerical solutions of STEs, namely about Ito-Taylor series and Gaussian approximations. We will start with an introduction to different ideas behind the numerical approximations of STEs. Then we will continue the Gaussian approximations of nonlinear STEs, which are based on the mean and covariance equations considered during the last lecture. Then we will introduce Ito-Taylor series of STEs by first considering Taylor series of ODEs and then proceeding to stochastic case by replacing the Taylor series with the Ito-Taylor series. Then we will derive numerical methods based on the Ito-Taylor series approximations of STEs. Finally, we will summarize the lecture. Let's now start with the introduction to basic ideas behind the numerical methods. So Gaussian approximations are based on approximating the mean and covariance equations of nonlinear STEs that we already considered during the last lecture. To make them practical, we need to do something called Gaussian assumed density approximation. This is because the expectations involved in the mean and covariance differential equations cannot be computed without knowing the probability distribution of the state, and because we don't know it, we need to approximate it, and one way is to use Gaussian approximations. Statistical linearization is also related to these approximations of STEs. In more general numerical simulation of STEs kind of methods, we have something called Ito-Taylor series, which are extensions of Taylor series to stochastic case. From that, we can derive something called Euler-Maruyama method and the Milstein method, which are the first order methods which generalize the Euler method for STEs. We will also consider a bit higher order methods based on the Ito-Taylor series. But next week, something called stochastic Runge-Kutta methods are introduced, which are also based on the Ito-Taylor series. Other methods, which we are not covering during the lectures, are approximations of higher order moments, as well as approximations of Fokker-Planck-Kolmogorov or PDE, but you will see some of these examples in the exercises. Let's now proceed to Gaussian approximations of nonlinear STEs. So consider this kind of stochastic differential equation, which is dx is equal to f of x and t times dt plus L of x and t d beta, where beta is a Brownian motion with diffusion matrix Q, or spectral density matrix Q. The mean and covariance differential equations, which we derived during the last lecture, are now given like this. So the time derivative of mean m is equal to the expectation of f of x and t, where the expectation is taken over x. The time derivative of covariance p is equal to the expectation of f of x and t times x minus m transpose, plus the expectation of x minus m times f transpose, plus the expectation of L times Q times L transpose. Now the catch in these equations is that the expectations are with respect to the actual distribution of x, which is p of x and t. And we need to recall that this distribution is the solution to the Fokker-Planck-Kolmogorov equation, so it means that we cannot really solve these equations without solving the Fokker-Planck-Kolmogorov equation first. We can now write down the mean and covariance equations explicitly, which say that the time differential of mean is equal to the integral of f of x and t times p of x and t over x, and the covariance consists of three integrals, where we are integrating over the p of x and t. Now in Gaussian assumed density approximations, we make a simple approximation by assuming that this p of x and t can be approximated as a Gaussian distribution with the same mean and covariance. So we actually replace that p of x and t in the above equation with that Gaussian distribution. If we substitute that Gaussian distribution to the equations, we actually get a solvable set of differential equations, which looks like this. So the time derivative of mean is equal to the integral of f and x and t over a Gaussian distribution with mean m and covariance p. Because all the terms in this integral are known, we can in principle compute this integral. Of course, we still have the trouble of actually expressing the exact value of this integral with arbitrary m, p and f, but anyway, in principle we have all the ingredients to compute the integral. For the covariance we have three integrals which also involve terms which we can in principle write down And provided that we can actually compute these integrals over the Gaussian distribution, we can compute the right-hand side and then solve the equation in principle. We can also rewrite these equations in a bit more convenient form by defining that En of g is equal to the integral of g over the Gaussian distribution like this. Then these mean and covariance equations can be written in this more compact form. So the time derivative of mean is equal to the expectation n of f and xt, and the time derivative of p is equal to the expectation of x minus m f transpose plus f times x minus m transpose plus LQL transpose. And the expectations are with respect to the normal distributions. But now these equations can also be simplified a bit. We can quite easily derive the following kind of result by integration by parts. So the integral of f of x and t times x minus m transpose over a Gaussian distribution with mean m and covariance p is equal to the integral of Jacobian over the normal distribution times the covariance. By using this result, we can rewrite the mean and covariance equations like this. So the mean equation is exactly the same as before, but the covariance equation now looks like this. So the time derivative of the covariance is the covariance times the expectation of the Jacobian transposed plus the expectation of the Jacobian times the covariance plus the expectation of LQL transpose. So we have replaced two f times x minus m kind of expressions with Jacobian in the covariance differential equation. We now conclude that we can actually use the Gaussian assumed density approximation differential equations for approximate solving of SDE, provided that we can compute the following kinds of Gaussian integrals. However, we cannot expect to be able to compute these integrals in closed form because we have arbitrary nonlinearities in our equations, but certainly we can approximate these integrals numerically. But now we can borrow those numerical integration methods from filtering theory. The most simple approximation is to linearize the drift term f around the mean as follows. So the approximation that results from this is that f of x and t is approximately equal to f evaluated at mean and t plus the Jacobian evaluated at m and t times x minus m. We can also approximate the expectation of the diffusion part by replacing x with the mean. This approximation results in the following linearization approximation of an SDE. So the time derivative of mean is approximately given by f evaluated at mean and t, and the time derivative of covariance is equal to the covariance times the Jacobian transposed evaluated at the mean and t plus the same Jacobian times the covariance plus L evaluated at m times q times L transpose evaluated at m. This is also the prediction step of something called extended Kalman filter. Actually, the continuous discrete version of the extended Kalman filter in filtering theory. One way to deal with the Gaussian integrals is to use integration rules for explicitly approximating them. For example, the Gauss-Hermite Cubic rules have this form. So the integral of f of x and t over the Gaussian distribution is approximated as a summation of wi times f evaluated at xi's and t. These something called sigma points are upskis as xi, and the weights wi are determined by the integration rule. For example, in multidimensional Gauss-Hermite integration, uncertainty transform, and cubature integration, we select these xi's to be equal to the mean plus the matrix square root of p times xi, where the xi's are also determined by the integration rule. The matrix square root is here defined to be p is equal to the square root of p times transpose of the square root of p. Typically, the square root is taken to be the Cholesky factorization of p. These vectors xi are indeed determined by the integration rule. In Gauss-Hermite integration, the vectors and weights are selected as Cartesian products of the one-dimensional Gauss-Hermite integration, whereas the uncertainty transform, which arises in filtering theory, uses these xi's. So xi 0 is 0, and xi i's are to the directions of coordinate axes like this. The weights are selected so that we get up to third order polynomials right with the integration rule. The Cubature method is a special case of the uncentered transform rule, which uses weights like this. So the lambda is set to 0. The resulting mean and covariance differential equation approximations then look like this. So the time derivative of mean is given by the numerical integral of f of x over the Gaussian distribution, which is approximated as weighted sum of f's evaluated at m plus square root of p times xi I. And the time derivative of covariance p is equal to 3 summations, which corresponds to numerical integrations of the corresponding terms on the right-hand side of the equation. This kind of rule is also used in continuous time versions of the uncentered Kalman filter, as well as in continuous time versions of the Cubature-based Kalman filters, which are also called Gauss-Hermite Kalman filters, Cubature Kalman filters, and many other names.